So I'm Jonathan. Today I'm going to be talking about creating image decoders in Rust.
Not sure you're turned on.
Yeah, it should be green.
Yep, good.
Okay. So as I'm going, feel free to stop me, ask questions. It's much more fun if it's interactive. If something's confusing, feel free. We can talk about. There'll be code samples. We can. So let's get started. So goals for today. I'm going to give a little bit of background about ImageRS, kind of what it is. Then going to be talking about, first off, what is an image format, and then how do you use them and decode them, and then more on, well, once you are decoding an image, how do you make it fast? So the ImageRS organization, there's this crate on crates.io called Image. It was started actually all the way back in 2014, which actually predates crates.io. The first version is not on crates.io. It was on GitHub, never uploaded to crates.io. I was not around at that time, but I joined later, became first a contributor, then a maintainer. At this point, it's not just the image crate. There's a whole bunch of other crates. You can see there's a crate for PNG, there's a crate for TIFF, for GIF, for WebP files, and a whole bunch more. And just one other thing to highlight, this is made by volunteers. It's not some company's product. It's not corporate funded or anything. This is people volunteering their time, collaborating, and over time, and literally hundreds of people have contributed, building something kind of incredible. So, stepping back, what is an image file? We're going to be talking today about raster image formats, as they're called. In one of these image files, you have a grid of pixels, where each pixel is storing the amount of light associated with that point. So lower numbers, 0, 0, 0, means black. The highest value, frequently these are 8-bit integers, so 255, 255, 255 means white. And there's a lot of complexity that goes into this as far as transforming these three numbers into every display has slightly different colors, the way things work. So even like this display and what you're seeing are not quite the same. There are ways to represent in image files all of that. We are not going to get into that level of complexity today. And one other detail is that in a lot of image formats, you don't want to store these values uncompressed. They take up tons of space. It would be really wasteful. So we're going to be thinking about how do we compress these values, make them take up less space. So the overall structure of an image format is generally going to have some sort of header that describes overall details of the image. Things like the width, the height. We said frequently they're 8-bit integers. They don't have to be. In the header, it specifies what you're working with. Then you have some pieces of metadata. This is what I was talking about earlier. How do you interpret the colors? But also other kinds of things. Maybe the GPS coordinates of where the picture was taken, the serial number of the camera. There can be some very sensitive things in pictures if you aren't paying attention. So always worthwhile to mention that kind of thing. And then finally, the bulk of the bulk of the file is going to be pixel data. And that's these individual values. Generally, they're arranged in a specific order, which is the top left pixel is first, then you proceed across right, so the top row of pixels is in that order, and then rows appear consecutively. But different formats do have their own ways of doing it. So now I'm going to talk and focus in a little bit on a specific file format, on PNG. PNG is a fully open format. It's extremely widely used. I'm sure most of you probably are very well familiar with the format. But internally, it's has a lot of modern features, but is actually way less complicated than you can imagine some other formats are. And another point is that for ImageRS at least, our PNG decoder is both really widely used, slightly horrifyingly widely used, and is extremely performant. It's actually faster than the reference implementation in C, which is kind of surprising. So to look a little bit at how Huffman coding, or how PNG uses compression to store its pixel data, it's this concept of Huffman coding, or Huffman compression. The idea here is that we are going to have a set of symbols. Each symbol is going to be converted into a code word, they're called. And a code word is a series of bits. Common symbols get shorter code words. Rare symbols get longer code words. And by looking at each code word, or even just the sequence of bits that are coming up, you can tell how long the code word is going to be and what it is, and that lets you tell you where the next one might start. So for English text, we have this little example on the slide. The letter Q is pretty rare in English. So if you have a Huffman code to compress English, Q is going to get a long series of bits. And then common letters, vowels, U, and E might be very short codes. So if you were to encode the word Q, which has this first Q that's very long, and then other letters that are much shorter, it'll appear something like this. This is all hypothetical, but kind of gives you an idea of what we're doing what we are doing with a Huffman code. And now, that was a little bit of textual description, but this is a Rust meetup, so let's look at some Rust code. So here, we're actually seeing a full implementation of a Huffman decoder. So it is surprisingly little code required to actually decode this. This is the core loop. There's other details you'd have to work out for the implementation, but we can actually walk through and kind of see what's going on here. So we see at the start, we have this structure called table entry. And the idea here is that's going to tell us about an individual symbol. So it has what the symbol's value is, and it has how many bits that symbol is. So we're going to have a table of these that we'll look up into. And now we get to the decoding loop. And the first thing we're doing in the decoding loop is we need to read some bits. Since we have a stream of bits, we have to read them. So we have this loop variable that says the number of bits we currently have. If we're less than 12, then we need to read more into our bit buffer. So if you're familiar with bitwise arithmetic, we have this next line that's a little bit complicated. But what it's doing is it is ORing the current value of the bit buffer with a new U32 that we have just read. So we read 4 more bytes of input, and we are going to OR the bit buffer with this 32 additional bits shifted by the number of bits that are currently in the buffer. So can anyone tell me what the result of this will be? Where are the new bits placed in relation to the old bits?
Higher order bits, most significant bits.
Yes, they'll end up above the bits that are already in the buffer. So what we end up with is 32 more bits, so n bits is incremented by 32, and now we have somewhere between 32 and 43 bits in our buffer, and we can start using that to find out what the next symbol is going to be. So I have this variable table, and it's not actually declared in this code, but what it's doing is we're indexing into table by bit buffer, but we've got this ampersand and then a hexadecimal value. And so what's happening here is that OXFFF is 12 bits of ones. So the lowest 12 bits are all 1. And then the upper bits are all 0. That's how in hexadecimal each character is 4 bits, and we have 3 Fs. So the end result is that we have extracted the low 12 bits of our bit buffer, and we indexed into a table. And now, the tricky part I'm not showing on the slide is how do you build a table that will have the values we want. But once you have that table, the actual decoding process just requires you to look with these 12 bits, and it tells you both what symbol did you get and how many of the 12 bits did you use. So you might not use all 12 if the symbol was short, or maybe you do use all 12. But either way, we find out how many bits we've used, shift those off of our bit buffer, decrement our count, and say we've got the symbol. So this is kind of the core decoding loop for Huffman, and as a result, when you're decoding a PNG, this is actually the bulk of the time is a loop like this. Go ahead.
Do you write this in Rust, or is this
Yes.
work doing in assembly?
No, this works out actually to be work pretty well in Rust. It compiles down. Go ahead.
I'm a little confused. If your symbol is less than 12 bits, and there's another symbol in your buffer after it, since it's compressed, aren't you doing a table lookup on multiple symbols at once, or what's happening?
Yes, you are.
Okay.
However, you can insert the same symbol at multiple indexes in your table. So every table index
Okay.
so if you had, for instance, a 1-bit symbol, half of your table indexes will be that one symbol.
Gotcha. Okay.
So it appears a whole bunch of times. But this trick means that once you've constructed that table, you don't have to do any fancy branches. You don't have to think, how many
Yeah.
bits.
You've given up memory in exchange for speed and size of the thing you're actually.
Exactly. So, yeah, I find this sort of decoding very cool. So once we've got our Huffman code, though, the next thing is what do these symbols actually mean? And I've been saying symbol. I haven't been saying byte. As you might guess, symbols can be more than just bytes. So our compression is either if it's less than 255, we treat that is a byte. We've got a new value. If it's more than 255, we have special meanings that we give. So 256 actually says, I want to use different Huffman codes. And so that enables you to have a new block with different Huffman codes. Maybe one part of your image has one pattern, a different part has a different pattern. So that enables some very good improvements in compression if the distribution changes. But then the next thing, and this is what gives you a lot of the compression, is the concept of repetitions. So even higher values indicate that you want to be copying previously seen bytes. So you had some bytes you've already decoded, and then you say, remember those previous bytes? We're going to grab, 3, 4, 200 of them, and we are going to repeat them afterwards again. And so this does not show how you're getting the distance, but you get a length from one Huffman code, and then you actually run a Huffman decoder again, get another symbol, and that symbol says how far back in the stream you should go to start copying bytes. So you have two symbols, and it ends up being this for loop that you can see, where we got a length, we've got a distance, and byte by byte, we copy one after the other. And there's a little bit of optimization that might go into that so that you don't have quite as many dependencies there, but this is the core idea. You're copying byte by byte. And then there's one more big step. Now that we've gotten our individual bytes, we've sort of seen that we want lots of patterns in those bytes, and we want them to be very predictable. The easiest thing to compress is all zeros. If everything is 0, it's great. If almost everything is 0, that also works pretty well. Since our repetition strategy, we can keep repeating that same 0. If you have 100 in a row, it only takes a few symbols to encode. And PNG has a trick on how it can make it more likely that these symbols are 0. And the way it does that is called filtering. What you're trying to do is for each individual pixel, instead of saving the red, green, and blue values, you save a prediction, or you don't save a prediction. You make a prediction, and then save how wrong your prediction was from the value you predicted. So a simple predictor is maybe the previous pixel is a good guess. So you just save how different is the current pixel from the previous one. So if you have an image that's, I don't know, all blue, all the same color blue, you save it in the first pixel. And then the next pixel says, oh, just remember that previous one? And you write 0, 0, 0 for all the differences. And now you've got a way to get all zeros, which you can compress really well. There's some fancier prediction strategies too. I think the ones I've shown are the previous pixel and the pixel above. Those are two of the strategies. A third strategy is you average those two, and so forth. So that was kind of a very quick overview of the basic pieces of PNG decoding. But the other thing is we'd like to make it fast. And so there's a big disclaimer here, which is the way that you make something fast is you benchmark it, identify what's slow, and make that faster. So I should not just be giving you the conclusions from that process. I should be walking you through actually doing the process, but I am going to skip ahead and give a few actual learnings and actual specific optimizations. So the first one is, we actually, on a previous slide, we had this loop. If n bits is less than 12, then do something, otherwise don't. The problem here is that that is very unfriendly to the branch predictor. The CPU, every time it gets to that instruction, has to guess, are you going to take the branch or not? Are you going to need more bits in your bit buffer, or do you already have enough? And the way Huffman works, it's on average you can guess how many bits per symbol, and so it's maybe every 5 or 6 or whatever it would be, but that's really hard for the CPU because it's just going to keep guessing wrong. It's going to say, oh, every 5, and then it'll be every 6, and so you don't want to have an unpredictable branch like that. We can improve it by having a different strategy for reloading our bit buffer. And then unconditionally saying it's full. So this might require more reading. We have to do more work, but it actually ends up being faster because we're not interfering with the processor's branch prediction.
Question. Is the primary metric, or like the only metric you're really caring about here, is like decoding speed, or are like other things also in consideration that you're going to talk about in like 2 or 3 slides?
So the highest priority is correctness. There's absolutely no use in being fast if you're wrong. But provided that it's correct, then I guess our next priority is kind of maintainability. So a slight improvement in speed at the cost of maintainability or at the cost of just being unworkable for future changes would also be rejected. But we do pretty much, once we've factored in like those sorts of factors, it really, we're trying to be as fast as possible. Since that is kind of a big comparison point, is going to be, are you able to match a competing decoder? Are you going to, and one of the weird things that actually happens is that it's not generally one specific image, it's one like number overall, you can say we're 5% slower than this, or we're 10% faster than this other library. Every image exercises different code paths ever so slightly, and can find some adversarial input that, like, some specific operation, you could be an order of magnitude slower, but only 1 in 1,000 images hits it. And so there's a lot of challenges there too, of how do you identify specific points? How do you deal with trade-offs? One image gets faster, another gets slower. So it's more complicated than just saying that, but
Yeah, isn't there an instruction you can use where you pre-calculate what the value would be, and then on the instruction it applies it or doesn't?
yes, conditional move.
Could you repeat the questions, please?
Sure.
yeah.
So the question was, isn't there an instruction you can use that tells you whether or not, or that lets you provide both values and then decide whether or not to use it?
Yeah, avoiding the cache.
Yeah. And so there is an instruction called conditional move. It works out that you don't need it for this operation. And the reason is because you can implement a bit buffer in a way where you're ORing in the same bits again and again. So rather than having a condition on refill, you simply OR the bits in the right place, and those bits will already be set if the bit buffer was full. So it becomes a no-op, but you don't need a conditional move to accomplish it. So then the next optimization, the next point, is around SIMD. And this is one of the pieces that people frequently jump to as, how do you use SIMD to make it all fast? And some parts of decoding you can't use SIMD for. The Huffman decoder that we were seeing, it's sequential. You get one symbol at a time.
What is SIMD?
That is a good thing to say. So SIMD stands for Single Instruction Multiple Data. They are a series of instructions that modern processors have that let you process multiple pieces of data at the same time. Frequently that can be 128 bits, 256 bits, even 512 bits of information. Almost an entire cache line, all at the same time. And so that's operating on much bigger amounts of data than a single U32 or U64 would be. And so that's frequently faster. One of the challenges, though, is that stable Rust doesn't have a safe API for using SIMD. Or this doesn't have a stable API that you can use exclusively with safe code. However, it turns out we can actually get pretty far without actually literally writing any SIMD code, because we can write for loops that the compiler will be very smart, look at and say, I can use SIMD instructions to implement these. So we have an example on the slide that at the top we're individually operating on 1 byte at a time. Each byte depends on something that is bytes per pixel, so a variable amount before the byte you're updating. So that's hard for the compiler to reason about because it doesn't know what this value is going to be ahead of time. Instead, we can, and this comes at a cost, we can individually have different implementations for every possible value that an image file might have. And we know from the PNG spec that there's not very many of them, so it's tolerable. But what this means is when the compiler sees, oh, look, 3 bytes ahead, or 3 bytes previously, all of a sudden, now this is an operation where it can identify that individual consecutive bytes don't depend on each other. So this is kind of a way that we can get a little bit more performance just by guiding the compiler in how it can use SIMD.
Question.
Sure.
Is array bound checking an issue in any of this code?
So that's actually a good point.
The question?
Is array bounds checking a problem in any of this code? And so that's one thing that I should probably also mention to make this auto vectorization friendly, is that when you use iterators in Rust, frequently what happens is you say, I want to iterate until we get to the end of this array. And what that means is the compiler can say, well, if you're only iterating till the end of the array, you're never going past the end of the array, so I don't have to do any checks until then. I just figure out how many iterations do I need, and then I can go until then without any bounds checks. So yeah, that's very important to make sure that you're writing code in a way that you aren't getting a bounds check every loop iteration. That would definitely destroy performance. And then one final approach that we would like to use, but actually cannot at the moment, is we'd ideally like to be able to use multiple cores of your computer. A modern processor might have 4 or 8 or 16, tons of CPU cores. They could all independently be running code. But at the moment, we're only able to use one of them for decoding a file. And the reason for that is because these different stages have the dependencies on immediately preceding data. So we don't necessarily know any future point that doesn't depend on previous data. There might be points in the file that are just so different, or maybe even the encoder was friendly and just didn't need to use any previous data. But without some indication of, hey, starting at byte 5000 in the file, you actually don't need anything before it, we don't have any signal out of band to say, how do you find the right point to jump to? So this is something, it's actually, the PNG file format is not set in stone. There's continued standardization work to actually make improvements to the file format. Backwards compatible additions that can improve PNG files that are created going forward. And so there's been ongoing discussion actually about embedding more metadata in the file, describing different points that a multi-threaded decoder could jump to that would enable each thread to decode in parallel. So this is something to look out for. So hopefully we'll see that in the future. So let's see, I can wrap up. Just quick overview. As we were saying, image data stores pixels. It's in encoded form. Our job as an image decoder is to reverse the encoding steps that created those pixels. And in PNG, that means we have to do Huffman decompression. We have to expand these repetitions of previously seen bytes. And we have to do an unfiltering pass to recover the actual values of those pixels. So hopefully this convinced you that image codecs are actually kind of fun. And happy to take any other questions if you have them. Thanks.
In what scenarios would the speed of an image decoder have a real world effect?
So in what scenarios would this, you say, as an image decoder have a real world effect? Oh, would the speed of an image decoder have a real world effect? Yes. So one case is for a web browser. You're browsing to a different website, and the time it takes to load actually impacts your experience. It impacts how much power your device uses, and it would just be nice if the images loaded faster. And so the amount of processing power that's required depends. Another factor is that maybe your software actually just has a requirement on particular level of performance, and you're thinking about what library to use. If there's a library in C that's one particular speed, and you're thinking, well, am I okay with using that library? It's got lots of unsafe code. That's very popular writing codecs in C to have tons of unsafe code, tons of assembly. There's been some very critical security vulnerabilities in image codecs, actually. caused by this. But if you're writing an application, you have to decide, well, but can I tolerate the performance loss, potentially, of switching to a codec in a different language? And so if you can match the performance, all of a sudden that concern goes away. And now you can bring safety as a improvement.
So the FFmpeg project, written in C, does video formats. It's wonderful, but it also has the complexity of a whole operating system. Is the project you're on headed in that same direction? And if not, what are you doing to kind of keep control of things?
So I would say that the project started with a...
Sorry to say this, but could you try to summarize
yes,
that?
I will. Yes. So the question is that FFmpeg, as a software product, has tons of C code and has grown extremely large in complexity. Have we been thinking about this as well? And the answer I would give is that the project started with an almost quixotic goal of decoding any image format. And somehow it is held together. We decode a huge number of formats, and actually have pretty strong decoders for many of them. So I think it's a goal to keep going on with that, to keep making improvements. And I think it's the sort of project that will never be finished and will never be complete, but it's still a lot of fun and it's held together.
Yeah, I just have a question about image codecs versus video codecs. Like, I'm old enough to remember motion JPEG, right, where they just stack a bunch of JPEGs together and that's what your camera would give you. Obviously, they're much more advanced today. Is there an intersection? Is there a future, right, where this library moves it also into video, or is there a sister library that has the same aspirations for video?
So the question is that there's also video formats that share a lot of similarity with image formats, and this I would answer that there's actually somewhat of a blurred line. PNG, for example, officially in the very recent spec update, but de facto, actually a long time ago, has an extension called APNG, animated PNG, and that allows you to store multiple frames in the same file. Our library does decode those multiple frames, so we have animation in that way. I don't imagine that the library will go on and support all sorts of video formats, mostly because modern video formats are even more complicated than many of the most complicated image formats. So one of the ways you can make an image format is you look at a video format and you strip out a bunch of stuff and then you package it up. So the AVIF format, for instance, is exactly that. They took AV1 video. They said, we don't need these things about multiple frames, about a frame depends on a previous one, and we have there's things called deltas, and it's very confusing. We'll strip that out, describe something simpler. That's AV1, or that's AVIF. So our ability to support even AVIF as this very complicated format is more limited. So I don't think that we will go to the point of saying we have a full AV1 codec anytime soon.
You mentioned that there's different filter strategies you could use. Does PNG or any format, do they all sort of in the standard hard code the list of strategies you have, or do any of them try to let you put code in the image, but hopefully not kill us all?
So the question is, are the list of filters hard coded, or can they be extensible in an image? So for most formats, they are hard-coded, but not all. And so JPEG XL actually has this concept of a decision tree that you can embed into the image that is run per pixel to figure out which prediction strategy you use and how you predict the previous pixel. So
And that's faster?
Oh, it is not faster.
But is it smaller?
But it is smaller, yes.
Okay.
So that was their goal.
So
You had-
JPEG XL is smaller.
Yes.
That I would agree with.
That's fun.
So do you think that was a good idea?
I'll reserve judgment on whether that was a good idea. So you had your hand up too.
Yeah, how fragile is the SIMD translations that come from code that's not SIMD? How brittle?
We've had, so the question is how brittle is the auto-vectorization? We've had somewhat mixed results there. We have had regressions at some points, so that has been trade-offs. We actually did also have a regression in some handwritten SIMD code too, in a very bizarre case, but yeah, it is a little bit more tricky than handwriting this, a little bit more tricky to get consistency than handwriting the instructions. But that has trade-offs both ways. It means that as the compiler improves, usually it finds better instruction sequences or better cost models for the processors, and it improves. But occasionally an LLVM update and it can no longer find the same instructions. So it is a trade-off. Yes?
Yes, in the SIMD code, you had the iterator as chunks mute. Is that the key to turning on the SIMD, or is that just something I'm adding in?
So the question is, I was using as chunks mute in the SIMD code, and that actually does help a lot.
Okay.
So yeah, that.
It's like a hint.
Yeah, it's a hint. It basically says I'm breaking this into blocks, and then I'm iterating over the blocks, and that's a signal that the compiler should also operate on those size blocks. And as chunks mute tends to work better than at, let's see, so as arrays, am I saying that right?
There's an array, I was just looking it up, there's an array chunks.
Yeah, so that is much more recent and works better, the as array chunks, I think, versus as chunks, which has been, the as chunks is actually what was more brittle for us. And so switching to a different strategy is how we got back this performance. Let's see.
What's the most complicated format you guys support? Why is it so complicated?
So the question is, what is the most complicated format we support, and why is it so complicated? And so I'm somewhat torn. There's a few of the more complicated ones, and we support them at different levels. So I'd say the most complicated that we have like kind of fully in-house support for is WebP. So this is a file format that has both lossless compression, which is kind of what we were talking about today, also lossy compression, which are basically independent inside the file format. So there's just two pieces, and they say, if you want to decode these files, you have to implement both. And then simultaneously, they also have not just one set of Huffman codes at a time, they have up to, 2 to the 16 different sets of Huffman codes that are used on different blocks. And the different, and also the different channels. So red, green, and blue pixels get different Huffman codes. So you have to alternate between as you're reading the image. They have a larger number of filters. PNG has 4, WebP is like 12 or 13 different. So yeah, they can get more complicated too.
This is a little bit off topic, but are the slides written in types?
So the question is, are the slides written in types? And yes, they are. So types is a, I think it's actually, is written in Rust, if I'm not mistaken, is a typesetting program that you can use. And I've been wanting to try it. So this was an opportunity to try out actually a Rust program for making slides. So I guess one more question.
When you run your benchmarks, what platforms are you benchmarking on? Are your benchmarks actually running continuously, or is it just on a per performance improvement PR basis?
So the question is, do we have kind of a benchmark platform that we're continuously running them, and kind of which systems are we considering? This is an area that I would love to be more sophisticated in. At the moment, it's kind of on a per PR basis. When you're working on a PR, you run the benchmarks. If it's kind of affecting something that we think might vary, we try to get other contributors to also run it, or other people in the PR thread. You could imagine a lot more sophisticated ways of handling this consistency, since all sorts of things do matter. So, but there's limits to what we have resources for to build and to maintain, and well, just to have. So, all right, thanks everyone.
In a former life, I worked on image formats, and I was part of the team that created JPEG XR, not L, R. And I was actually invited to Lausanne, Switzerland by the JPEG committee, because it was like, ta-da! I think that was the second or third attempt to replace JPEG. It also didn't go anywhere, sadly. And so there's a long history all the way back to JPEG 2000, and everybody's trying to make a better JPEG. And this format just will not die. So JPEG is still king. All right. All right. Thank you for that, Jonathan.